I heard you guys had a good time with the sub yesterday. Very glad to hear about that. Rave reviews. You were very helpful to her, and she really enjoyed her time. Well, Placido got shot again. Okay. Oh, I'm glad that's on camera. Okay. So, all right. Quick question for the beginning of the day. You don't have to write these down because you don't have a semester exam. When does an object moving in a straight line have angular momentum not equal to 0?
All the time.
Yeah, basically. Whenever you want it to. Remember that example we did where you could pretend there's like a radius from some point? So yeah, the answer would just be whenever you feel like it. Yeah, exactly. So today we are going to talk a little bit.
It's okay, honey.
That's why. Mr. Hathaway, were you conducting seances in the back?
No, I don't do those during the week. Thank you. Conservation of angular momentum is the phrase of the day today. Which toy? Oh. Do you still have that with you? Okay, let's wait till after notes and maybe we can go get it. Yeah.
So the other week you said Yahoo, and I want you to know that I've used Yahoo quite a lot now.
I said Yahoo?
Yeah, you said Yahoo.
Huh. I don't usually say Yahoo. Was it in like a weird accent, or was I just saying it?
So you said Yahoo, and I go to Katie, I'm like, so I think you went Yahoo. Yeah.
Yeah.
Hi, Kylie, and hi, Potter.
Yeah. Hi.
Miss you.
So dying.
Okay.
She's got a concussion.
She was here yesterday.
So?
I'm going to use this to demonstrate angular momentum.
Why are you doing it like that?
All right. Watch this.
Careful!
All right. Now, what do you suppose is going to happen if I make the radius of this circle smaller? Noah says faster. Anybody want to say slower?
No,
It's going to spin faster or slower.
no, it's tangential velocity will be greater.
Okay, let's find out. Yeah, so it does get faster and faster and faster as you decrease the radius. Maybe I got to go a little bit faster. Here we go like this, and then...
There we go.
So then you can see as the radius goes down, you've got a much quicker velocity.
So the regular velocity goes up, and the tangential velocity stays the same.
They're both going to go up. Yep. The number of revolutions per second will go up, and tangential velocity might stay the same because on the outside you'd be spinning slower for the same tangential velocity that you'd have by spinning faster on the inside. You don't have to write that down. Yahoo. But we do have to make sure that we know what's going on here and why it's behaving this way.
Oh.
Angular momentum is L, and that equals R times momentum P, which is equal to RMV, or RM. Yes. So when we are talking about angular momentum then, and it being conserved, that means that the momentum at the beginning has to be equal to the momentum at the end.
You could just make like a 3 up 10 and just a line up and it would look like R&B.
I missed
Sorry,
that.
looking at my handwriting.
Keep going? Okay. I'll listen to Katie. I do like the picture over there too, by the way. Who drew that? Nice. So, if we want to figure out how velocity is related to these other things, You know, we can just, let's quick cross off the masses because they suck. So if I want to solve for v, I would get rid of this r by dividing both sides. So, if we look at this relationship, you can see what happens here. If you take, so these two are like constants. On the bottom, this is the radius that we're changing. If you make this radius larger, that makes your velocity smaller. And as you make this radius smaller, it makes your velocity bigger. So it's an inverse relationship. That's why we saw what we saw with angular momentum being conserved.
I'm sorry, my head is everywhere.
Now I actually want you to draw what I just did. But instead of having you draw it, I actually drew. I printed out my notes and I cut out this for you.
You get his
Paste these
drawing?
into your notes
Yes.
Yes!
Glue sticks.
I would be happy to autograph these at the end of class.
Okay.
I will hold you to that.
Okay.
Do you have a glue stick on you?
A glue stick?
No need for glue sticks, my friends. I am looking out for you. I have 40 pieces of Scotch tape right here. So feel free to take 2 for this, and then you'll take 2 for something coming later on.
Wow. I'm genuinely impressed.
That was some setup.
I feel like I'm getting a treat.
You're setting the bar for your future self very high.
So yeah, just if you want to take the 4 right away, you can. Just make sure it doesn't crumple in on itself.
Was the powder intentionally left there to distract me from the tape?
That's flour from astronomy. We were making craters today.
Okay, so now, before I take this out,
And actually, I'll pass out the next thing too.
I'm very concerned about my placement of this tape.
I'll let you know where to put it. As much as I would have loved to have you guys draw this, and as much as I would love to try and reproduce it myself on a whiteboard,
That is
no thanks.
fantabulous.
Oh, wait, should this go in here?
Yeah, I'll let you know in just a sec. Yeah, what I passed out first will go near what you just put in your notes.
This is great.
Yeah. Did I miss anybody for the thing here? Good. So the first one I passed out is going to go next to these notes here. And then the next one you are going to put in with a large blank space off to the right or to the left where you're going to put the next round of notes.
What about a ball?
What about a what?
A ball.
If you want to do that. You can title these notes Rotation of Solid Objects. Rotation of solid objects. That's what this example is going to encompass. I suppose those of you at home, I can put these up to the camera. Here's the first one I passed out. You're going to want to pause this and draw this in your notes next to the notes that you just did. And this one here is the next thing for your notes. And leave space next to this because that's what we're going to be talking about right now. That took a long time to draw when I first did this. Okay. So rotation of solid objects. Here's what we're going to be doing with the situation that you were just given. We've got this spinny thing here, also known as a pulley, and this big box, known as a mass, hanging off of it. And it's going to cause this whole system to spin so that the mass is going down. Our goal is to solve for a and alpha.
Egg and
Do you mean
alpha?
Jesus fish?
I mean Jesus fish.
Is it egg and alpha or egg and alpha?
In terms.
You forgot the D and.
Just put an apostrophe.
Oh, yeah.
You got too excited about the Jesus fish.
Yeah.
Maybe the Jesus fish was the D. And you're sawing for A and in terms.
All right.
So which one?
Grim.
Yeah.
For which one? The small picture or the big picture?
The big picture is the main one. The other two are just boiling that down further.
It could be like, in terms of grim, like, a lot of times it could be like, cabal, but like, yeah, never mind. I'm sorry.
Yahoo! So if we're going to solve for these two things in terms of those variables, what we want to start with is just trying to solve for these two things. And if we're lucky, they'll automatically be in those variables. Do you think they will be?
No.
No.
We'll find out.
I mean,
Only
Next time on Dragon Ball
at
Z.
least half of them, I would say at least 50% will be there originally
Mm-hmm.
somewhere.
All right. Well, we'll give it a shot and see where we go. So yeah, this one right here, that's just the system. This here represents the mass of the pulley itself, and then the tension force going down from the mass. And this block here is just the force diagram for the block itself that's going down. So again, for these problems, it's not just a matter of thinking about the mass that's pulling the pulley. We have to acknowledge that the pulley itself has a mass that makes it more sluggish to that movement. And that's what we have to take into account here. Okay.
So wait, is that like when you use like a 50-pound third cord or like a 10-pound third cord? Like that's the weight of the pulley that you're talking about? Like,
Yeah. Yep. So if I want to start this, one of the easiest and best ways to start all questions in this section is to take a look at what's going on with torque. So torque is equal to several things. You know, it's equal to radius times force. And in our case right now, as you can see from the picture, the radius is defined by capital R. So that's going to be capital R for our cases. And then T is going to be just equal to our tension force here, because that's the string that's pulling the mass down. So this would be the radius of the pulley. This is the tension force that the string is responsible for pulling that pulley. So that's part of torque. And of course, torque is equal to like a zillion things. So the second thing it's equal to is simply moment of inertia times Jesus fish, or alpha. So there you go. Because these are both equal to torque, we can set these two things equal to each other.
oh, this is actually kind of convenient because then you can just pull. Ah.
So yeah, let's solve for alpha. Divide both sides by the moment of inertia, and we have our final answer, only it's not final. Why is it not final?
Because we don't know.
Force of tension.
Yeah, tension force is not something that we're taking this with respect to. So somehow we got to work through this further in order to get to a good answer for the angular acceleration.
So we just
You just work out the force of tension to be something with gravity and mass and all that.
Exactly. So what should we do next?
Force.
Let's do a force diagram. And that's what's listed here for you. You know, you've got your tension force and you've got your gravity. What force is winning this battle here?
gravity.
Gravity. So in our force diagram for what's going on vertically here, we've got, when we look at all the vertical forces, we've got gravity winning, tension force is doing the best it can, and that's going to be equal to ma. And of course, if we want to figure out regular acceleration here, I can just divide both sides by m. And now we've got an expression for acceleration. Are we good with acceleration? No, because we still got that lame old tension force there that we have to somehow get rid of. So, it'd be nice if we could just erase it, wouldn't it?
I mean, technically we could.
Watch him do it. Watch him do it and tell us that that's right.
So, let's erase tension force. Oh, that would be great, though. So, we're kind of stuck here. And if we want to go further, what we have to realize is this tension force is the only thing messing this all up. Because force of gravity is just mg. And those are all things that we're okay with having in our equation. So if we can figure out a way to get tension force not equal to tension force, then we'll be in the free and clear.
Can
So-
we just go in reverse and put tension force to something else?
That's exactly where we're going with this. So there's a relationship between angular acceleration and regular acceleration.
Oh yeah.
Yep. So, let's do this, and then we'll have tension forces on both sides, and hopefully we can just get rid of them then.
I thought it was times radius is angular acceleration, not the other way around.
Nope, this is the way.
Yeah, okay.
Okay.
We're not so.
Don't erase your notes, I just erased mine.
Just to make a little bit more space.
So, acceleration is equal to radius times angular acceleration.
And the radius is still the capital R, right?
Yes, yes. So let's see here. Acceleration was, well, mg minus tension force over m. So that's equal to radius times alpha. So the radius, as Sarah said, is capital R. So capital R times alpha, which is RFT over I. Remember, alpha was this. So if I multiply R times that, we get R squared FT over I. Are you with me?
Why would it is R
R times R.
Yeah, because remember alpha is equal to radius times tension force over I. So then if acceleration is radius times alpha, I got to multiply alpha times radius. So multiplying this by r gives us r squared. So that's where that comes from. And that's about where the physics ends. The rest of this is just math. Because we've got tension on both sides, we should be able to get it in terms of everything else.
No, I'm a failure.
So let's do that. All right, I'm going to cross multiply here. We'll go through these steps. We might as well. Let's see. Let me know if I do anything wrong. So IMG minus IFT,
IMG Academy.
and then I'm going to cross multiply the M. So MR squared FT. So I want to get this over here, so I get the FTs on the same side, so I can eventually pull them out. That makes that positive. And I think the next step is just dividing both sides by what's in parentheses. Yeah. Yeah, we do.
We started doing this, and I'm like, I forgot what we're solving for and how this helps us. But now we got here, and I'm like, oh yeah.
Yeah. So now we got tension force in terms of G, R, I, and M. So all we got to do is put this back into our expressions for acceleration and angular acceleration, and we should be all set.
This is all wrong.
Yeah, I know. You guys got this. So, let's see.
So it,
And the way it's listed here might be a little different from the way I was writing it. I think I'll try and keep it the same here. So this was mr squared, right? And plus I.
Wait.
And that's all divided by m. And that's our answer.
Oh, never mind.
But you could put the mg over m subtracted by that
Oh, no.
quantity.
Yep. If you're not happy with this looking kind of messy, yeah, you can just destroy the m's. Goodbye, m's. Except for this one down here. So let's see. So that would be as nice as you could get that solution. Yes. Good.
Yes.
So, let's do alpha. I'm going to get rid of this.
Alpha is just RFT.
Just multiply the
Well, all you do is keep the r and I out and then just multiply by the quantity. Oh no. No.
Sorry.
So
All right. So that's what your angular acceleration would be equal to. And again, all we're doing, we did some basic math at the beginning, and the rest of this was doing less basic math to get ft in terms of everything else. And that's what this is up here. This is just your tension force. Now this too, I'm guessing Sarah's probably not happy with. So we can simplify this more, right? Absolutely. So, Placido, yes?
will FT always equal IMG over MR squared plus I?
No.
I'm done with this class.
Yeah.
Alright, I gotta go do all this stuff now.
Yahoo.
No, don't worry about it.
So if I want to cancel some stuff out here, I think I can get this up top and, 1 over I times all that. So...
Because you just put R
leave
over
him
I.
alone.
Because then,
He's shown his work. It's
because
okay.
I feel like then you can just multiply this I through here.
Yes.
So then it's... And then it's, for me, it's easier for me to see how to cancel these I's out. I get mixed up when it looks like this. So that goes away, that goes away, that goes away. And that's where you would land here. Yeah. But yeah. Do whatever math you're comfortable when you get to this point, but you don't have to simplify. This is just taking it an extra step. Oh, that was enjoyable, huh?
What do you see?
And we're not even done.
Wow.
This is probably, this plus what we did, what was it, last time? Two times ago, 2 class periods ago, is probably the hardest stuff that you'll encounter in this class. So, if you feel uncomfortable and mentally spent, that's okay.
I don't even know what we just did. I can't remember what we did.
Yeah, it's okay.
All I knew was that we saw
No,
food
it was like
and
5 years ago.
the sunset, I guess.
Yeah, come back to me in like 10 minutes and I'll only be able to tell you, oh, we had the word grin and letters before.
Next example.
I forgot about that.
Yeah,
I already forgot about that. No, I was stopping you from
That's
thinking of my friend, and then I saw that, and that made it worse.
That is our handshake.
Okay.
What's wrong with our handshake? What's wrong with our handshake?
What's wrong with their handshake?
All right, you're going to want to draw this in your notes.
They hate on our
Do
handshake.
we have a new title?
No, it's still rotation of solid objects.
I've got about 10 lines. Do I need to start a new page?
Nah, 10 lines should be enough. This isn't as bad as the last one.
I've given up on trying to save things.
What does that,
Is it the same
yeah,
object?
just wanted to say inside.
So, what this is it is a rod. This is a pivot point right here, and it is going to swing down like this. So we'll say that the total length is going to be L.
So it's like a trap.
Kind of. And when we're dealing with things that are rotating like this, what's really important is that we know where the center of mass of these objects are. Because if we're going to deal with this, with something like energy, it's important to know exactly how high above the ground this center of mass position
I'm
is.
very confused why it was centimeters.
Oh, no.
Mr. Hathaway, what does that say?
What does what say?
Something centimeters and what?
Oh, this is just cm for center of mass.
Oh, I thought that.
See, thank you.
We had it where it was cookies.
I like cookies.
Me too.
Are good.
Mr. J.
Are good.
And we'll just say this mass has a mass capital M.
Oh boy.
Oftentimes, when we're dealing with things that are rotating like this, we have to use capital M's, just like with the previous example.
Mouth.
Draw and write the problem.
I thought you were going to say you had drawn right at the same time, and I was going to say good.
Okay. So, we want to figure out angular velocity and non-angular velocity, also known as regular velocity, also known as tangential velocity.
Is writing considered drawing?
Stop.
I don't think so.
It's drawing of symbols.
Exactly.
So what is a symbol?
Stop.
Symbols just mean whatever you want.
Okay. So-
instead of using variables, we use numbers as variables. So like if I use a 5 instead of x, then we can use 5 to solve for another number.
So if we're going to go ahead and do this, the way to do this is energy. Because we don't have enough information. You know, we've got a few things, length and mass and center of mass. We don't have enough to deal with like torque or something. We don't have any mass. We don't have a certain distance, that there's some force being exerted. So energy is another way that we can solve some of the problems in this rotational motion chapter. And energy equals energy, exactly.
Wow.
So what is all the energy at the beginning? Potential or kinetic?
Potential.
Potential.
Shake me. Shake me.
At the end, it's all
I
kinetic.
expected to see this.
But this is not any regular kinetic energy.
Shake me.
Oh dear. This is rotational kinetic energy.
No!
Yep.
Stop.
So potential energy is m times g times height.
Stop.
So that's going to be m times g.
Where's the cookie jar?
And the height, this is the bottom. This is this is like the floor. This is the lowest point that this mass is going to get. The center of mass is down here. It's not going to go any lower. So the height would be L over 2 because it's starting half that length upwards. So mg L over 2. And we did notes.
Wait, can you explain that one more time?
Sure. So mg times height for the potential energy. The height is simply how high you are above the 0 point. And the center of mass represents where your object is actually kind of located. So if the center of mass is here, it's only half the length of the rod down. So you begin L over 2 high.
Question. What
Yes.
if it's a lollipop and the center of mass is not in the center?
That's more complicated, and we'll be talking about that tomorrow. Or actually, no, that's something that comes later on in the semester. Good question.
I like how it says lollipop, but it made sense.
And this is what rotational kinetic energy is equal to.
Yeah, pretty much.
So, it should be pretty easy to solve for angular velocity, but not quite, right? There's always going to be something that makes things a little bit more difficult.
Why do
There's
you
always
do
an
that?
easier way.
Mr. Physics.
So, this moment of inertia I, this is different based on the scenario that you're looking at.
When did God have to do this?
Page 286 in your textbook is where you can find these different moments of inertia. For our particular example, long thin rod, rotation axis through the end would be right here. So the moment of inertia I is going to be 1/3 ml squared. This is on page 286. Page 286.
It's a law. Abide by it.
No, there's so many examples I couldn't fit them all on the formula sheet.
So is it memorized?
in a problem?
Yeah, it would be given.
Oh, okay.
So 1/3 ml squared is what we have for this particular example for
Does no
that.
one else here said or who said that?
What?
Did you say that?
Say what? Martin Luther Square?
Yeah. I thought it was that.
Everybody gasped at the same time.
So let's see, 1/3 ml squared times omega squared. Okay, so there's our setup. If we want to solve for angular velocity squared, we just got to get it all by itself. So there's a lot of canceling we can do. Actually, this m should be capital, I guess.
Okay. Okie dokie.
I'm canceling this problem because of homophobic statements from a couple of these.
So,
What?
in order to get this omega by itself, let's get rid of some things. Masses go away.
Thank you.
This L goes away, cancels out with the square,
And then the square.
and this becomes a 6th. So we want to get this by itself. So
Well, couldn't
what
I
I'm-
just cancel out the halves and keep the third?
yeah, you could do that. So you'll end up with the same answer in the end. If we would make this into a 6th, then to get rid of this, we'd have to multiply both sides by 6. So 6 times 1/2 would be 3. So this would be 3g, right?
Yep.
And then over here we've got L omega squared. So this makes it a little bit easier now. So divide both sides by L.
Isn't that the thing that everybody's saying gives them coronavirus?
What?
And to get rid of the square, what do?
I
We erase it. Goodbye, square.
And then you just
It's
add.
all funny games because I tried that on my cup test.
I really want someone just to white out one of the problems.
What if I did on the exam? You gave me an A for effort, but an F for accuracy.
Failure.
So that would be your angular velocity there. 3g over L, all under the square root. And
That
finally,
was easy to find the velocity.
yes, why is it easy to find the velocity?
Because I
I just wanted to say that because you just do
I
a
just
thing
really
because-
wanted that to
Bezos
be
is
true.
stepping down
You
in
just
Amazon
do a
CEO.
thing because there's already the relationship that we
Oh, yeah,
Yep.
thingamajiggy.
Where's the relation?
What
It's
would
the
be
R, it's times.
Yep.
Yeah. It's
V
times L,
is equal to radius times angular velocity.
which is just what I said.
And what's our radius here, do you suppose?
L over 2.
L over 2.
Yay!
Jeff Bezos is stepping down as Amazon CEO.
I don't believe that. Finally.
Would you like to gamble? We will gamble across that.
So, that would be our velocity right there. And I suppose if you wanted to make this a little bit prettier, you could do that. Or you could leave it like this.
Yeah, so I'm not a very pretty guy myself.
I got a couple minutes, so I'll just do it anyway. So if I want to get rid of this L, I could put it under the square root, and then I'd have to square it as I did that. So that would be like 1/2 times 3GL squared over L under the square root, and then we can cancel junk.
He's gonna sell us stock. That's probably why he's doing it, so he can sell stuff.
So that would be the prettier way to write it.
Oh, that's just simplification.
Yeah.
Then don't simplify.
Yeah, you don't have to simplify. I just figured if you wanted to make it look pretty, and if our folks at home in the future want to make it look pretty,
There's a lot.
maybe simplification is made into a formal school law in the future, so that's where this would come in handy. Otherwise, if not, feel free to leave it as unsimplified as you would like.
There's a lot of things in life that we just don't have to do.
That's true.
I'm pretty sure I've made this comment before in this class about how, remember how way back when in like first grade, all of your math was just numbers, and now it's slowly been switching to letters.
I've definitely
The
said
amount
that.
of letters that we
You know, this is one of those things where you can take a picture of this, show it to your parents, and they'll be super impressed. Be like, look what we did in class. Now take me to Cops for some custard, please.
My dad would bully me
So
if I told
my
him.
mom is like, "Oh, you're taking AP physics, but I'm taking a welding class," and she's like, "That's so amazing! Like, oh my goodness!" And I'm like, "I welded a straight line, but I can do this." Like,
It's just a given to her that you can do this.
yeah.
give me that